Let's see examples here. So we have a system where we have the poles is located at -2 and -5. So I use poly function because I want to make the transfer function using TF. So TF requires polynomial, so that's why I use poly, because I know the value of poles. So I have the denominator here is 1, 7, 10, which is s squared plus 7s plus 10. So I purposely put the here the omega n square equals to omega n here 10. So I have this transfer function 10 over s squared plus 7s plus 10. So I want to plot the seesaw tool. So when I plot this transfer function 10 over s squared plus 7s plus 10, we have this kind of plot. So this plot is actually similar to the plot that we have seen in the previous examples in the camera and motor system, right? What I want to show you is that actually we can just play around with this red dot here. It is actually the closed loop poles. It depends on the value of k. So in this case, our k is actually the compensator c. C equals to 1. When we have our k equals to 1, this is the root locus looks like. This is the response of the system, step response of the system. So we can play around with this red dot here. You can just put it everywhere, whether on the this location, or you can put it on this location. So you can see when you play around with this dot here, it becomes the response, the step response of the system is change. It's change. You can see from here it is actually 2 poles on the real axis. We have overdamped system. So that's why the step response of the system looks like this. It is overdamped response. So when I put it closer to this breakaway point, the value of our k now is changed to 0.2, and we can find the poles that is located on this exact location. And then the system still overdamped because it is still located on the real axis. So when I put it this location where we have multiple poles at the same location, so in this case we have our k value is 0.225, and the location is actually -3.5. So the system becomes critically damped. So when I increase further to 0.5, let's say, so our systems becomes underdamped. It has underdamped response, and we can see that the overshoots increase from 0.132, and we can put it greater number of k. So the oscillations is now become clearer. The overshoot become 20% right now, and the location of poles is on the is a complex conjugate. The system is under damped response. We proceed with the next problems. Let's say I want to add additional poles. So I want to add real pole. Let's say we add at -1. Now we have additional poles at -1. Originally we have poles at -2 and -5. So now we have the third pole, which is actually at -1. You can see here the change of the root locus. Previously we have a root locus that looks like a plus symbol, right? When I add extra poles, now the system becomes third order system because we have 3 poles. And then the root locus bends to the right. So when I move the poles from -1, I move it to the left. So you can see the system root locus less bend to the right. So you can see from here. So I put it past -5. So let's say around -6. So you can see here the change of the shape of the root locus as well as the shape of the step response. So you can play around with the Cito tool and you can see the difference when we put the extra poles to the different location. So now our the closest pole to the j omega axis is -2. So in this case, our pole here is at -6. So you can see, delete this first. You can see here the overshoot of the system is 1.93%. So when I add real pole, let's say I add at -1 here, we can see the overshoot becomes 7.05. When I change to -6, it becomes 8.72. When I change to 20, it becomes 3.8. When I put it like 200, it becomes 2.07. So what we can see from this example here is that when we put the third poles that is far away from the poles that is near the j omega axis, we can see that the system behave like the second order system. So we have third order system in this example. Alright, so when we put -6, it is actually close to this -2, which it will affect the transient response. So remember last time when I tell you about the dominant poles, which is the pole that is near the j omega axis, and the dominant poles exist as long as the third poles located 5 times ratio to the left of the S-plane. So in this case, -6 and -2 is about 6 divided by 2 is only is only 3 ratio. So let's say that we put it 10. So the overshoots become 6.17, which is actually quite differ from the original 1.93%. So let's say we put 100. So this is very, very far to the -2. So we can see that the overshoots become closer and closer to the original response of the system with the second order system. What will happen if I introduce zeros to the system? Now we have a system, third order system with no zeros. Okay, we only have 3 poles here. Let's say we add a real zero to the system. In this case, when we introduce 0 at -1, it is actually cancelled out with the real pole at -1. So you can see the behavior of the system is like the original one. So let's say we move the pole located at -3, for example. You can see here the pole on this imaginary axis bend to the left. It is opposite to what we have seen just now. When we introduce poles, the root locus will bend to the right. However, when we introduce 0 to the system, the root locus will bend to the left. So, see, I just drag it to the right. It bends more to the right. The closer it is to the poles, the dominant poles, it bends to the more to the left. But if I bring the 0 far from the dominant poles, it bends less to the left. So let's say I just want to put it at -10. You can see here the effect of zeros is no more significant because it is actually like the original one. It bends to the right. So you can see when I drag the poles back closer to the dominant poles, the shape of the root locus it wants to bend to the left. Okay, so when I put it on -5, it will cancel out the real pole at -5, and this is the shape of this root locus.